Lesson 21 is solving rational equations. The word rational means something that can be written as a fraction. So if you see like rational equations, that usually means equations that involve fractions. And if we look at 21.1, it's simple rational equations. So within the like kind of group of rational equations, there's something called a proportion, which a proportion is when you just have exactly like one fraction equal to another. So if we look at example 1, 21 over 7x is equal to 105 over 315. So this is an example of a proportion because we have one fraction equal to another, and there's no other terms anywhere throughout the equation. Like I have nothing added or subtracted over here or over here. It's just that one fraction equal to that other fraction. Okay, so if you have a proportion, you can solve it by cross multiplying, which means that we multiply diagonally through the equal sign and then set each product equal to each other. So in example 1, 21 over 7x equals 105 over 315. The first diagonal, 7x times 115. Sorry, 105. I mixed up the two numbers. 7x times 105. And then the other diagonal through the equal sign is 21 times 315. So is equal to 21 times 315. Okay, so we took both kind of diagonals and took the like product of those two numbers and set them equal to each other. So we can simplify each side. If we do 7x times 105, I just need to multiply 7 times 105, and that's 735. And then the x just gets tacked on to the end. And then on the other side of the equal sign, 21 times 315 is 6,615. And then now my goal is to solve for x, so I just want to get x isolated. I have a 735 that is being multiplied by the x, so to undo multiplication, we divide both sides by 735. So 735 divided by 735, that is 1, so that cancels itself out, and then I'm left with just x is equal to, if I do 6,615 divided by 735, that is 9. So I'm left with x equals 9 as my final answer. So example 2, we have 4x over 50 equals 44 over 50. So this is another example of a proportion, so we can solve it the same way we did with example 1 by cross multiplying. But this is also kind of like a special case of a proportion because both of these fractions have the same exact denominator. So equations are just one way of saying that, like, the left side of the equal sign is equal to the other side, like they're balanced, they have the same value. So if we know that the numerators are, or sorry, if we know that the denominators are the same, they're both 50, then in order to make each fraction the same value, we just have to get their numerators to have the same value because the denominators are already taken care of, those are both 50s. So one approach is we can just go ahead and take the numerators and set them equal to each other. So 4x equals 44, and then my goal is to solve for x, so that 4 is being multiplied by x, so to undo it, I would divide both sides by 4. And then 4 divided by 4 is 1, so that goes away, and I'm left with just x equals 44 divided by 4 is 11. So our final answer would be 11. I want to talk about one more approach that you could take for this problem, if that way just didn't quite sit. So like I said, both the denominators are 50, so we just have to get the numerators to be the same to be balanced. So I know that like this numerator is 4 times x, like 4 times something that's unknown. So we can think, okay, 4 times what is going to get me to 44 is going to make it equal 44, and I would have to multiply 4 times 11 to get to 44, so that's why x is equal to 11. Okay, and then example 3, another proportion. All the problems in this section will be proportions, so we'll be able to cross multiply each time. So 9 over 3x equals x over 75. So same approach as example 1, we will cross multiply. So the first diagonal is 3x times x. So 3x times x is 3x squared. And then across the equal sign is the other diagonal. And if you want, like on example 1, I kind of wrote, 9 times 75, but if you can just go ahead and kind of put that product in right away. So 9 times 75 is 675. And then now I have an equation where my goal is to solve for x again. So my goal is to get x completely isolated. We need to cancel out that 3 that's in front first before I take care of the power. We don't follow order of operations here. It's almost like the opposite of it. If I were to try to get rid of the exponent now, I'd have to square root the 3, which would not do me very much good. So I'm going to go ahead and just try to get rid of that 3. So to cancel it out, I can divide both sides by 3 because that 3 is being multiplied by the x, and division cancels out multiplication. So 3 divided by 3, that goes away, and then I'm just left with x squared. And then 675 divided by 3 is 225. And then now still same goals to get x completely isolated, so I just have to cancel out that power. So the inverse operation of squaring something would be square rooting something. So I would square root both sides, and that would cancel out the power and just give me just regular old x to the first power. And then the square root of 225 is 15. But we have to consider that, when we're solving and we take the square root, we have to think about the positive and negative version. So it could be positive 15 as the square root of 225, but it could also be negative 15 as well. So we'd write it as positive or negative 15. And the reason is because this part of the problem is saying, I'm just going to rewrite it over here. So if x squared is equal to 225, we're asked for what values of x could make that work. Well, okay, so 15 squared is 225, but also if I take negative 15 squared, that's negative 15 times negative 15, which also turns into positive 225. So that's why both values work, the positive and negative version, because when you square it, it's going to turn positive. Okay, so x is equal to positive or negative 15. And then moving down to 21.2. So it's just more rational equations. These are still proportions, but they're gonna start to involve more quadratics. Example 3 kind of involved a quadratic with x squared from right here, but now we're gonna get into ones that we actually kind of have to factor to solve. So example 1, solve for x. X minus 4 over x plus 5 equals 14 over 22. So we still take the same exact approach. We still want to cross multiply. So the first diagonal, x plus 5 times 14. So I'm just going to kind of write that out. I'm not going to worry about multiplying it yet, but I'll do 14 in front because I'm going to have to multiply by the entire x plus 5. So I'd have to put that x plus 5 in parentheses. And then the second diagonal, 22 times x minus 4. So equals 22, and then same thing, it's being multiplied by all of x minus 4, so I put the x minus 4 in parentheses, and then now I'll have to distribute. So 14 times x, 14x, and then 14 times the positive 5 is 70, so plus 70. And then on the other side of the equal side, 22 times x, 22x, and then 22 times negative 4, so negative 88. And then now I still have a linear equation, so that means x to the first power, so I won't have to factor or anything, or take square roots or anything like that. My first priority is just to try to get my x's together on the same side of the equal sign. So it doesn't really matter which way you go, it's up to you. But we have a 14x and a 22x, so I think I'm gonna go ahead and subtract 14x from both sides, just so I don't have to deal with negatives. Again, it's just really personal preference. So 14x minus 14x, that cancels out the 14x over there, which is what we're going for. And then after that, I'll bring down the 70. And then 22x minus 14x is 8x. And then I also need to bring down the minus 88. And then now I have like my x's kind of all combined onto one side of the equation. So I'm just trying to work on isolating x and moving everything away from it. So we have two things that are being done to the x. The 8 is being multiplied by it, and the 88 is being subtracted. We usually undo addition or subtraction first. So that means that I would add 88 to both sides. So 70 plus 88 is 158. And then that's equal to, I bring down the 8x, negative 88 plus 88 cancels out. And then now still just trying to get x by itself, so I would, that 8 is being multiplied by the x, so to undo multiplying by 8, I would divide both sides by 8. So 158 divided by 8 is 19.75. I'm going to write it. I'm not sure if your workbook will ask for it as a fraction or decimal, so we'll do it both ways. So if I have, let's see, it'll be either be x equals 19.75, or if I need to leave it as a fraction, like in its most reduced form. It's always kind of nice to review that. So I'm going to leave it as 158 divided by 8, and then we just need to divide numerator and denominator by the same number in order to reduce it. So 158, we could divide both by, it looks like just 2, so 158 divided by 2 would go down to 79. So divide numerator and denominator by 2, so 158 divided by 2 is 179, and then 8 divided by 2 would be 4. So kind of unsatisfying, but x equals 19.75 or 79 fourths. I'm going to go ahead and just erase this middle part and kind of clean up that answer a bit. Okay, there we go. So x equals 19.75 or 79 fourths. I know sometimes they kind of go back and forth depending on what form they want your answer in, so it's always good to have both ways. Okay, so moving on to example 2, this is when the cross product is a quadratic. So 7 over x minus 2 equals x plus 3 over 12. So same thing, we have a proportion, we're going to approach it the same way, we're going to cross multiply. So the first diagonal is x minus 2 times x plus 3. Since those have multiple terms in each like factor, I have to put them in parentheses. So x minus 2 times x plus 3. And then the other product, or the other cross product, is 7 times 12. So 84. And then, unfortunately, like, so when we solve by factoring, we set each factor, like, we have it factored, and then we set each factor equal to 0. That only works when you have 0 on this side. So like I can't just take x minus 2 and x plus 3 and set them equal to 84. It's a specific property that requires you to have 0 on the other side. So what that means is that we have to like multiply this out and then subtract over the 84 and then refactor. So if you feel good on that, just work ahead of me and check your answer at the end. I'm going to go ahead and FOIL. So we multiply the first term in each parentheses. So x times x is x squared. And then the outer x times 3 would be a positive 3x. And then the inner terms, negative 2 times x is negative 2x. And then the last terms, negative 2 times 3 is negative 6. And then I bring down my 84. I have to check for like terms. So I have this 3x and this negative 2x that I can combine. So I would bring down my x squared. 3x minus 2x is 1x, but we don't have to write the 1 in front. And then I'm also gonna, my goal is to get a 0 on the other side of the equal sign. So to save us a little bit of writing, I'm just gonna go ahead and subtract over the 84 right away just to cancel it out over here. So negative 6 minus 84 is negative 90 because they're both negative, so we can just add them and keep it negative. And then 84 minus 84 is 0. Okay, so in standard form now, it's x squared plus x minus 90 equals 0. So now we have a quadratic. We have methods for solving a quadratic. I would like to say I hope all the problems you'll see in this section will be factorable, But remember, there are like other methods of factoring quadratics if you just like truly don't want to factor it, or sorry, other methods of solving quadratics if you don't want to factor it. There's like the quadratic formula, or completing the square, whatever you want. But in this problem, since a, like the coefficient of x squared is 1, when we go to factor it, the like x squared term, the first term, breaks down into x and x. And then the way that we fill in the remaining like parts of the parentheses is we need numbers that multiply to c, which is negative 90. That's a multiplication sign, not an x, sorry. And then add up to b, which is 1. So multiply to negative 90 and add to positive 1. So that combination, we would definitely have to use like a 9 and a 10. And then 1 would have to be negative to get them to multiply to negative 90. And then to get them to add up to a positive 1, we'd make the smaller number negative, so the 9. So this would be a minus 9 and then a plus 10. And then now it's factored completely. And now we have a 0 on the other side of the equal sign. So we can set each factor equal to 0. So one factor is x minus 9. So do x minus 9 equals 0. And then the other factor is x plus 10. So x plus 10 equals 0. And then my goal is to get x by itself. So I would add 9 to both sides right there and end up with x equals positive 9. And then for the x plus 10 to get x by itself, I would have to subtract 10 over. So I would end up with x equals negative 10. So x equals 9 and x equals negative 10 as my final answers for this problem. So last problem, example 3, is just an example that has what's called extraneous solutions. I know we've talked about it a few times throughout the year, but it's just essentially solutions that don't work for the problem. So x squared over x minus 5 equals 25 over x minus 5, so we'll approach it the same way we have with the rest of them. We'll cross multiply. So the first diagonal is 25 times x minus 5. And if you're getting to the point where like you feel comfortable distributing it in without like kind of writing that first step, that's totally fine. So I'm going to write it all out though. It'll be 25 times, it's being multiplied by all of x minus 5, so since there's multiple terms, I need to use parentheses. And then the other diagonal, x squared times x minus 5, so x squared times x minus 5. And then now we want to kind of try to get the equation simplified, so I'm going to go ahead and distribute. I don't have to FOIL anything here because I just have the one term by those binomials. So 25 times x, so it'll be 25x, and then 25 times negative 5, so it'll be negative 125. And then over here, x squared times x, so x to the third power, and then x squared times negative 5, so negative 5x squared. So we don't have a quadratic here, but we do have like a polynomial, so we'll probably have to end up factoring it. So first thing is to try to get it in standard form, so everything on one side can equal to 0. So I want to kind of keep I would at least prefer to like keep this is going to be my lead coefficient, like the x cubed. I would just prefer to keep it positive. So I'm going to subtract over these two terms, subtract slash like add. So minus 25x to cancel like that part out. And then I don't have any like terms over here, so I'm just going to subtract it like off the end kind of. So minus 25x. And then I want to cancel out the negative 125, so I have to add that over. And then same thing, I don't have any like terms on the other side, so it just kind of gets like tacked on to the end. That way just like everything is on one side of the equation. So this would be like a 0 because I canceled everything out on that left side, and then x cubed minus 5x squared minus 25x, and then plus 125. And then now I have a like polynomial that has 4 terms. So when we do 4 terms, we do factor by grouping. So you always want to check for a GCF first, which none of these terms have a common factor other than 1, so I wouldn't factor out a GCF here. I would just go ahead and like break the expression in half, or not the expression, but break the like right side of the equation in half, and then I would factor the GCF out of each half. So 0 is equal to I'm going to stop here too, because if I wait till the end, I'll forget. But this method of factoring, if you watch this example and you're like, I don't remember how to do that, it's called factor by grouping. So that way, if you like kind of wanted to search any extra examples on YouTube or something, you would know what to search. Just search factor by grouping. Okay, so the first half of this side of the equal sign is x cubed minus 5x squared. So between those two terms, the greatest common factor, the GCF, would be x squared. So when I pull the GCF out of each term, I'm like dividing it out of each term. I'm kind of like distributing it. So x cubed divided by x squared, that would leave me with an x right here. And then negative 5x squared divided by x squared would leave me with a negative 5. So that part's done. And then I can move on to the second half. So over here, negative 25x plus 125. In most cases, when the first term is negative, I like to factor out a negative. Also, like, keep in mind, we've done this a few times now, like, we want what we end up with in parentheses, like after we factor out the GCF, to mirror this. And my first term here is positive, so I definitely have to factor a negative out to get this to turn into a positive. So between negative 25x and 125, the GCF is going to be negative 25. And then I'm like undistributing that, so like dividing it out of each term. So negative 25x divided by negative 25 would leave me with a positive x, and then 125 divided by negative 5 would leave me with a negative 5. And then this next step's really important. You have to check to make sure that each of these are exactly the same. So same numbers, same terms, same signs, and everything. So that's where, like, don't write this part, but if I had like factored out just a positive 25, it would have left me with negative x plus 5, and that's not okay because it's not the same exact thing as the other parentheses. So kind of like you need to go back and double check it. Okay, so now what we did is we just basically created like two kind of weird big terms. So there's that first one that is underlined and that second one, and they both have a common factor of x minus 5. I'm going to pull that x minus 5 out of each. Okay, when I pull it out of each part, like each of the blue underlined sections, I have some stuff left over. I have this x squared and I have that minus 25. So x squared minus 25, that becomes its own binomial factor. So the double parentheses that goes there, it doesn't become like x minus 5 squared or anything. We're just pulling it out of both. And then when we pull it out of both, the remaining parts become their own factor. And then we want to check to see if we can factor it any further. X squared minus 25 is a difference of squares, right? So like a difference of squares, that's like something in the pattern a squared minus b squared, and 25 is a perfect square. That factors into a plus b times a minus b. So then, because this is, so x squared minus 25 is 5 squared, my like a would be just x and my b would be just 5, and I would put it into this formula to factor it. So this would be 0 equals x minus 5, that first one, just that stays the same, that copies down. And then the x squared minus 25, a is going to be x, b is going to be 5, so I'd factor into x plus 5 times x minus 5. So that's our like completely factored polynomial. I'm going to go ahead and I didn't realize I was kind of running into the second page, so I'm going to copy this up here. If you have room below it, you can just continue below it. But now I want to set each factor equal to 0. So I do x minus 5, set that equal to 0. X plus 5, set that equal to 0. And then this like x minus 5 is the same factor as this, so we don't need to do it again. And we're not graphing it, so like that's where like that multiplicity word would come in, but we don't have to worry about here. It's just a double factor. We don't have to do it a second time to get the same answer. So for the first one, x minus 5, I would have to add the 5 over to isolate x. So this would become an x equals positive 5. For the second factor, x plus 5, I would subtract the 5 over to isolate x. So it would become an x equals negative 5. So x equals 5 and x equals negative 5, those are solutions. However, one of them is extraneous. So extraneous means like something that doesn't really work for this problem. So with rational equations, and this is true of all of the problems that we've like kind of solved so far, but we just haven't come across this case yet. There's a lot of opportunities for extraneous solutions because of the fractions. So like with a fraction, you can't have like any number, like say if I had 7 over like 0, you can't have a 0 in the denominator. Like that's a big no-no. It makes the fraction undefined. I can't believe I just said big no-no, but it makes the fraction undefined. So like if I say that one of my answers is x equals 5, but if I were to go check my work and put that into the original problem, I'll get zeros in both denominators because 5 minus 5 is 0. So that means that x equals 5 is extraneous. Okay, if you ever come up with a case where both of your answers end up being extraneous, that would mean that it's no solution, technically. But that x equals -5, that still works, because if I did like -5 minus 5, that's -10, which is not 0, so we're okay. I'm going to go back really quick and just backtrack through the last few problems. So technically, like, there is the opportunity for extraneous solutions in any rational problem. We just didn't really end up with any that would. So like if we look at example 2 from 21.2, like the last example we did, the only thing in the denominator, there was an there was an x minus 2 right here. So like the only answer that would be extraneous would be x equals 2, but we didn't get that answer, so we don't have to worry about that. And then like same kind of concept over here, there's an x plus 5 in the denominator. The only answer that would end up being extraneous is like if we ended up with an x equals -5, but we didn't for that problem, so there is no extraneous solutions. Okay, so extraneous solutions are just answers that you may end up with, or that you do get that happen to make the denominator equal 0. You just kind of cross them off on your scratch paper or know in the workbook that they are extraneous.